Good morning, everyone. Welcome back. So the one thing I just wanted to start off today with was a brief summary of the midterm that we just had. I know Sam went over a little bit of it tutorial yesterday. What I wanted to do is I just wanted to mention a few things about it. So overall, it was done quite well. So you can see here that for the total on the midterm, the mean score, the average score was 86%, and there's a distribution. So it was quite nice. There was a lot of students that got 100%, and quite a few of them that were quite close. So this is really nice to see. The breakdown of the questions. Question 1 was done really well. Question 2, there was, of course, some issues. The troublesome question there was the very last one, the counting the number of elements that had a particular order in, I think it was in the alternating group. So that one caused a little bit of trouble. But other than that, it was quite well done. Question 4, I'm skipping question 3 right now. Question 4, the 15 puzzle problem, very well done. See, 53 students got perfect on it, which was really nice to see. So that one was really good. Question number 3, that was the one that caused some troubles. The break, sort of 60 to 100, is that for the Rubik's Cube question, the second one, there was either if you knew what to look for, you got it, and if you didn't know what to look for, you didn't really make much progress. So it was sort of a all or nothing kind of question. In fact, it was all or one, because I think most people ended up at least getting 1 point on it, because there was something showing there about what potentially to look for, but there was some flaws in the reasoning. The part A question, which was show that the product of two even permutations is even, that one was reasonably well done. This spike here at the 60 is because a lot of people got that one correct and then made minimal progress on the second part of the question. So it was the Rubik's Cube one that was the challenging one. So have a look at these solutions. Make sure you've got an understanding about why it's true, why these moves are impossible, and how we can use the parity results to get at them. And if I wrote on your assignment, there's a fundamental flaw in the reasoning, then make sure you really understand where the fundamental flaw is coming from. A lot of it had to do with claims of moves are even, but the position is odd. And the fundamental flaw was that the position wasn't necessarily odd based on the labeling that you provided. So the whole argument breaks down if you're trying to show something's impossible when the parity argument doesn't work in that case. So make sure you have a look at that and see that you do understand it now. So all in all, very well done. Congratulations. The point moving forward here is that we are starting to get into some more abstract concepts. So to make sure you keep your momentum going, keep up to speed, make sure you're understanding each lecture as we go through it, and you'll see similar performance on the second midterm. I do want to warn you that in the past, students have found this to get slightly more challenging as we go along, because the first midterm was more about calculation techniques and results associated with those. Now we're getting into slightly more theoretical results. And so you want to really focus on structure here. Structure, less on computing and more on structure and patterns. And so today's lecture is going to take this sort of to the extreme. We're going to look at structure and patterns within some of the groups we're familiar with. So last day we introduced the groups of units modulo n. So this is given an n, a number n, it's forming the group of integers modulo n. And so that means we're looking at multiplication as our operation. So we had to throw a bunch of stuff away. We basically had to throw away anything that had a common factor with n, because we weren't going to be able to have inverses for such things. So once we throw away all of the numbers less than n that are going to be problematic for us, what we end up with is this group called U sub n, or the group of units, and we've just kept only the numbers that are relatively prime to our modulus, relatively prime to n. So we did some examples. U4, keep only the numbers less than 4 that are relatively prime to it. That's 1 and 3. U5, keep only the numbers less than it that are relatively prime to it. That's 1, 2, 3, and 4. And similarly for U8. U8, we made this observation that every non-identity element has order 2, because when you square it, you get the identity. I want to point out, as I said in the past, I kind of want to point out on various classes where there is potential for a project. And so I want to point out something here that's potential for a project. So let's just look at this Cayley table, and wherever I see a 1, I'll write an E, just because I want to be a little bit more general here. So there we go. And then for 3, 5, and 7, I don't really care that those are 3, 5, and 7s. All I really care is that they were just different objects. And so I'll call them X, Y, and Z. And then I'll put them down here as well, X, Y, and Z. And then I'll just do this sort of mapping of wherever I see a 3, I'll put an X, a 5 is a Y, and a 7 is a Z. So this was X, Y, Z. This is X, Y, Z. This is Z, Z, Y, Y, X, X. And so what this is it's a collection of 4 objects, X, Y, Z, and an operation of multiplication on them. And it's coming directly from this U8. So we know it's a group. It's going to be associative and everything because it's just the pattern of U8. But here we're looking at structure now. I'm saying, forget the fact that it was 1, 3, 5, and 7. All we cared about is that if I took a 3 and multiplied by a 7, I got a 5. In other words, if I took X, multiplied it by a Z, I got a Y. This is a group that has the exact same structure as the U8 group. In fact, it's the same form, also known as isomorphic. So this is where we don't really care about what the labeling was, just the underlying structure. And so this would be a representation of a group that is isomorphic to U8, has the same structure as it. This is known as the Klein 4 group. Klein 4 group. And it turns out that this group, so it's got 4 objects in it, that's where the 4 is coming from. Every element is its own inverse. So every element is order 2. The inverse of X is X, the inverse of Y is Y, the inverse of Z is Z. That's the E's down the diagonal. Every element is its own inverse. But it turns out that this group has a really cool application. And the really cool application, it's got lots of applications, but in the context of this course, our focus is on understanding puzzles, etc. So an application of this is to a game called Peg Solitaire. I don't know if you've ever played a Peg Solitaire game, but it's one of these games where you got all these pegs in a board, and if you pick up a peg and you jump another peg, then you remove that peg from the board. And the idea is to be left with only one peg on the board. So you sort of do this frog hopping kind of game. And I used to play this game all the time in Hope. When we used to go on family vacations, we'd stop at a little diner in Hope. So it's sort of a little city sort of northeast of here. And at the diner, there'd always be these little Peg Solitaire games on the table. And written on the side was like, if you leave 3 pegs, you are, well done, you're bright. If you leave 2 pegs, well done, you've shown immense skill or something. And then if you leave only 1 peg, you're a genius, and blah, blah, blah. And so the idea is to just jump pegs and see if you can be left with only 1. It turns out that you can do a full analysis of that puzzle using just this group called the Klein 4 group, and it's just this multiplication and that. So that if you're interested in a application of some of the things for a project and you don't have a project in mind yet, it's worth looking into peg solitaire, group theory. You'll find some reference papers. I might even have one on the website already. But anyways, that's that. So with the unit groups, you know, we've got a set of objects, we've got a way to combine them. We know what the identity is, it's 1. Natural question to ask is, what's the inverse? What's the inverse of an element? So for example, in the U8 group, every element was its own inverse. So what's the inverse of 3? It was 3, and so on. But in the group U5, up above, what was the inverse of 2? Well, we'd have to track that down from the table. We'd say 2, oh, there's where the 1 appears. So the inverse of 2 is 3. And the inverse of 4 is 4. So what we would have is that 2 inverse is 3 here, and therefore 3 inverse is 2. The inverse of 4 is 4. So we can see that from the table. Is there a way to figure this out without using the table? We think back to the additive group. I'll scroll all the way back, group of integers. Here we are, the group of integers, mod n. What we could notice is that, say in, well, actually I wrote it down up here. Here we are. We knew that there was a simple way to get inverses, additive inverses. You just take the modulus and you take away the element from it. So what's the inverse of a? It was 12 minus a. So that was quite simple to get an inverse in the additive group. In the multiplicative group, though, it turns out to be a little bit more challenging. How do we get the inverse of an element in the multiplicative group? Well, it turns out we actually have the tools. We covered these tools already in our number theory, introduction to number theory. And so let's just look at some results. So if I have two numbers, a and b, which are integers, and d is the greatest common divisor of them, then we know that there has to be a linear combination of a and b that is equal to their greatest common divisor. So this was the extended Euclidean algorithm. We can always find a linear combination of a and b that results in their GCD. So in particular, if the numbers are relatively prime, we can always find a linear combination of them that gives us 1. So here's the example down below. Suppose I'm looking in the group U8. So I'm up above and I'm looking at U8. And I want to find the inverse of 5. Well, the first thing I do is say, well, 5 and 8 are relatively prime, because that's what it means to be in U8. So I already know they're relatively prime. So I can find a combination of them that's equal to 1. 5 times 5 minus 3 times 8 is equal to 1. Now, if I take that equation and I take its result modulo 8, then I have that 5 times 5 is congruent to 1 mod 8. And when I take it mod 8, I just get rid of anything that's got a multiple of 8 in it. And so that means that the inverse of 5 is 5. Oh, sorry, I don't know why I wrote 5 to the 1. The inverse of 5 is 5 in U8. So that means in general, if I want to find the inverse of an element in UN, what I have to do is, if I want to find the inverse of A, is I just use the Euclidean, extended Euclidean algorithm on A and N. And then whatever number is returned right there in the extended Euclidean algorithm, that's the inverse. So we can use Sage Math for this. And I'll just bring it up here. I'll just bring up the cell server because I just want to do a quick, sorry, I'll resize it. I just want to do a quick calculation. So I don't need to bring up the full Jupyter implementation. So for example, if I wanted to find out, so let's say, what is the inverse of 6 in U17? So that's what I'd like to know. What is that inverse? So I'm making sure I got the right comment box. There we go. Yeah. So I've that little hash tag in front, or pound sign, is just telling it not to evaluate. This is just a comment. So what is the inverse of it? Well, what I'll do is I'll do x GCD of 6 and 17, and I'll evaluate, and it returns the GCD, which is 1. That's what I expect, because if it's in the U group, it has to be relatively prime, and then 3 and -1. So that tells me that 3 times 6 minus 17 is 1, or in other words, 3 is the multiplicative inverse. So inverse of 6 is 3. And so that's how we can use SAGE to find these multiplicative inverses. We actually use the XGCD algorithm, so the extended Euclidean algorithm. Let's do that 5 in U8 one, just because there's an extra step that's sometimes required. So if I go 5 and 8, then I evaluate. This tells me that the GCD is 1, which is great. And this tells me that -3 times 5 plus 2 times 8 is 1. So I'll scroll that up a little bit. So what's that telling me? It's telling me that, I'll try to get it in the background here, that another equation we could have written down is -3 times 5 plus 2 times 8 is equal to 1. Or in other words, so that's what we get from the XGCD. Or in other words, it tells us that -3 times 5 is congruent to 1 mod 8. Oh, I just buried that behind the window here. But that's fine, because -3 is congruent to 5. So I could always just replace the -3 with a 5. Right? They're congruent. So what I would have done is just taken -3, added 8 to it to get another number that's congruent to it that I can use instead. So I take whatever values returned from the extended Euclidean algorithm, I just shift it so that I get the number that's congruent to it that is positive. And so that way I just took 8 plus -3 to get me the 5 that I needed. So we can use the extended Euclidean algorithm to get these inverses in our U groups. So that's all I wanted to finish up with this, is that for the U groups with multiplication, everything's pretty much the same as addition. You're just using multiplication now. You just have to throw some numbers away because they don't have inverses. And then to find the inverses of the numbers that you do have left, you potentially can use the Euclidean algorithm to find those. Well, not potentially. You can always use Euclidean algorithm, but you might be able to find them through other ways, like above. We worked out a table of values, so we could just read them off the table of values. All right, so now what I'd like to do is get into chapter 11, which is subgroups. And I want to get this done today because the homework assignment is, of course, related to this. But I want to just preface this with saying this whole section is about patterns. It's just about trying to recognize patterns, to not so much focus on nitty-gritty calculation, but to take a step back and just see what kind of patterns can we spot. And we'll see that if we can spot patterns, it makes life a lot easier in terms of the calculation. We're not blindly calculating things anymore. We're looking for higher order structure and patterns that we can exploit. So the first thing I want to introduce is the idea of a subgroup. And that is, if we've got a group G, and we've got a subset of it, let's call it H, then if H is also a group under the same operation, then we call it a subgroup of G. So what do I mean by it's also a group? I mean that H is a subset that is closed under multiplication, all the inverses are in there, and it contains the identity. So if it's some subset that also obeys the properties of a group, then we call it a subgroup. So for example, this set H consisting of the 3-cycle 1, 2, 3, the 3-cycle 1, 3, 2, and the identity, that is a subgroup of S4. Why is that? Well, it contains the identity. Yep. What about closure? Is it closed? Well, we have to check that all products are in there. Well, anything times the identity is just whatever we started with, so that's automatically in there. So we just have to work out the other products. So what about if I squared this thing? 1, 2, 3 times 1, 2, 3. I get 1, 3, 2. That's in there. Good. What about if I took 1, 3, 2 and multiplied it by itself? So 1, 3, 2 times 1, 3, 2. That's 1, 2, 3. Good. So at least the square of every element is in there. What about the mixed product? 1, 2, 3 times 1, 3, 2. Well, those are inverses to each other. So that's the identity. And so that's in there. So yeah, it's closed. Every possible product I can take with those elements is in there. So it's closed. And that means that this thing is a group. So what else do we need? We need to know, is the identity in there? Oh, sorry, the identity. We already did that. Inverses. Are inverses in here? Inverses. Yeah, well, the inverse of 1, 2, 3 is 1, 3, 2. And the inverse of 1, 3, 2 is 1, 2, 3. Yep, so those are in there. So perfect. The identity's in there. It's closed. It's got inverses. So it is a group. H is a group. Satisfies all the properties of being a group. And since it was a subset of S4, we call it a subgroup of S4. What about this next one? K. K consists of these 3 elements. Identity, 1, 2, 1, 2, 3. It's not a subgroup because it's, for example, not closed. 1, 2, 3 times 1, 2, sorry, 1, 2 times 1, 2, 3. If I take the product of those 2 things, then what do I get? I get 1, 3. And that's not an element of K. So it's not closed. Also, it doesn't contain all inverses. For example, the inverse of 1, 2, 3 is 1, 3, 2, and that's not in K. So there's another reason that it can't be a subgroup. So if we're trying to show something's not a subgroup, we just really need to violate one of the things. Is the identity in there? Oh, yep, it is in this case. Is it closed under products? Nope. I found 2 that multiplied together that it wasn't in there. So not a group. So we're done at that stage. Or maybe you're looking for inverses. You're like, is this thing a group? Well, let me check the inverses of everything. Inverse of identity is the identity, it's in there. Inverse of 1, 2 is 1, 2, it's in there. Inverse of 1, 2, 3, oh, nope, that's not in there. So not a group. So you really only need to check one of these things. So therefore, K is not a subgroup. So we're mostly going to be interested then in subsets that are also in and of themselves groups, in which case we talk about subgroups. How can you check that a given set, like we've done above, is a subgroup? Well, there's something called the 2-step subgroup test that allows you to do a quick check. What the 2-step subgroup test is, I'll just resize this. Actually, nothing's being covered by my pen, so that's fine. The 2-step subgroup test just says, check to see if all products are in there. If it's closed under multiplication and part B, it's closed under inverses, then it has to be a subgroup. So instead of checking 3 conditions, we only need to check 2. Closure under products, closure under inverses. And the reason is we get the identity for free, because if A is in there, then part B says the inverse is in there, and part A says the product is in there. So an element times its inverse is the identity, so the inverse has to be, or the identity has to be in there. So we can eliminate having to check the identity if we just check closure and inverses. Okay, so what this means is that this gives us a nice way to actually generate subgroups, to build subgroups. In order for a group to be a set to be a subgroup, we just need to make sure it's closed under products and it's closed under inverses. So that means the way we're going to build our subgroups is we are going to take a collection of elements in our big group, whatever our big group is, we take a collection of elements and we just form all possible products and all possible inverses of those products. And that is going to be the subgroup that we call the subgroup generated by, so it's the subgroup generated by these things. The way we represent it is we use these angle brackets, and these are read generated by, well, subgroup generated by. That's how we read these angled brackets. So we're saying the subgroup generated by G1, G2, G all the way up to GK is equal to all possible elements in the group, which can be written as some product of the G's with some powers that can either be positive or negative, inverses or just regular powers. Okay, so that's a bit of a mouthful in terms of how we define the subgroup generated by these things. But the idea, the plain language is it's just all possible products, all possible inverses of those products. We put those together into a set. That's our subgroup. So let's go through a few examples of these. Here we've got S3. I'd like to know what is the subgroup generated by, remember these are these angle brackets, what's the subgroup generated by 1, 2? That is, what is all possible products and all possible inverses of the products of this, well, this one element, 1, 2. So I write down 1, 2. And then I've also got to write down its inverse. Oh, but it's already 1, 2, so that's already there. And then I have to write down its square. Oh, but that's just the identity. And then I have to write down its cube and the inverse of the cube and so on. All possible powers of all possible products of everything involving 1s and 2s. Well, that's just, this is it. It's either going to be the 2 cycle or the identity. That's all we're going to have. And so the group generated by the element 1, 2 is just this subset consisting of the identity and the 2 cycle. Similarly, for the subgroup generated by 1, 3, it's just all possible powers of that thing, which is going to be the 2 cycle or the identity. And similarly for the 2 cycle, 2, 3. What about the 3 cycle, 1, 2, 3? Well, it's going to be all possible powers of it. So it's 1, 2, 3. The square of it, which is 1, 3, 2. The cube of it, which is the identity. And so that's all we get. Now you can see that this notation is identical to the notation we used for cyclic groups. I'm going to scroll back up to, oh, I'm going to have to do it. Sorry, it's the next, or the previous notes. So one of our groups that we introduced in the previous chapter was this idea of cyclic group. Here we are. We said the cyclic group in a group G, or G is cyclic if there is one element that we can power up to get all the elements in the group. And we use that angle bracket notation down here. We're just extending this idea now. We're saying that a cyclic group is one that's got one element that generates all the other elements in the group. But we can look at more general types of subgroups where we take any collection of elements and just take all their possible products and inverses. And that's the subgroup generated by them. So a cyclic group is generated by one element. All right, let's have a look at this next one. What about the group generated by these 2 elements, 1, 2, 1, 3? Well, they would have to contain 1, 2, 1, 3, the product of 1, 2, 1, 3, which is 1, 2, 3. What else would it contain? Well, it would contain 1, 2 times 1, 3 times 1, 2. That would also have to be in there. That's just all possible products. But this is equal to 2, 3. So it's got that 2 cycle in there. And it would also have to contain 1, 3 times 1, 2, but that is equal to 1, 3, 2. So it has to contain that one. And it's also got to contain 1, 2 times 1, 2, which is the identity. And we know we're done because we've got 1, 2, 3, 4, 5, 6 elements, and that's all of S3. So what this tells us is that the subgroup generated by 1, 2, 1, 3, these two cycles, is the whole group. So that means that we can create any permutation on 3 objects by just using 1, 2 swap and a 1, 3 swap. So this is an observation. Is it always there is some I such that alpha to the I is equal to alpha to the -1? You are absolutely correct. So if alpha to the I is equal to alpha to the -1, that's equivalent to saying alpha to the I plus 1 is the identity, which the smallest value that kills it is the order. So the order of alpha is I plus 1. So that means, is there always an I such that alpha to the I is alpha to the -1? Yes. I equal to the order of alpha minus 1 will do it. 1 less than its order will be that number. So if the order of an element is 10, then alpha to the 9 would be its inverse, because alpha to the 9 times alpha is alpha to the 10, which is the identity. Yeah, good question. All right, so if you look at this one now, you can kind of see what we're doing is we're introducing structure, a sort of higher brow way of looking at things. But this immediately tells us stuff about, for example, swap puzzle on the first day of classes. This tells us that if we just look at the swap puzzle with only 3 tiles, that swapping the contents of any box with only box 1, that's our legal move, is we have to use box 1 and any other box, that's enough to generate all permutations of 3 objects. So in other words, the 1, 2 swap combined with the 1, 3 swap is enough to generate all possible permutations. And you've heard me just use the word generate, and that's the nature of this word generate here, is that we're looking now at a subgroup generated. So what are all possible positions that are generated by using the 1, 2 cycle and the 1, 3 cycle? You can get all permutations. So this is now putting a formal language around observations we had in the past. So how about this group, this subgroup, the one generated by 1, 2 and 1, 2, 3? Well, the first thing to note, I'm not going to put my equal sign there because I want us to think in terms of higher order structure and not necessarily the calculations. I could write down it's 1, 2, 1, 2, 3, and then the product of them, and keep generating all possible products as I can. See if I get everything. The first thing, though, I'm going to do is I'm going to note that if I multiply them together, then I already get 1, 3. So 1, 3 is already in this subgroup, and 1, 2 is already in there. And I already know that once I have a 1, 3 combined with a 1, 2, I can get everything in S3. That's just the previous line. So 1, 2, 1, 2, 3 gives me all of S3. I don't even need to do any more calculation than that because I build it on a previous result I already know. Once I have 1, 3 is that 2 cycles in there, and 1, 2, that 2 cycles in there, then all possible products of those ones give me all of S3. Okay, so let's continue looking at these kinds of subgroups. So we've got, oh, maybe I should point out one thing first of all. This is about language. So what is the size of this subgroup? Well, it was size 2. Now it's cardinality. It had 2 elements in it. That is actually equal to the order of 1, 2. And when I talk about size of a subgroup, we use the word order for the size of a group. So I would say this group has order 2 because there's 2 elements in it. But notice that the order of the 2 cycle 1, 2, the other use of the word order which was how many times you have to raise it to a power in order to kill it, it's order 2 as well. And that's really the reason why we can use order in two different contexts and not cause confusion, is because they actually give the same result. The order of an element, that's our classical use of the word order. What do I have to power it up by to kill it? The order of an element is precisely the order of the group it generates. It's how many elements it's going to create when you power it up. And so we get that same thing here. The order is 2. And I'm free to just write order as 2 because you can say, well, do you mean the order meaning the size of the group? Yeah. Do you mean the order, which is the order of the element? Yeah, because they mean the same thing in this context. So there's no ambiguity as when I use the word order here. And then, of course, with this one here, an order 3 element produces or generates an order 3 subgroup. Now you might think, does this work for more than one element? So that next, this set down here, I'm using 2 elements of order 2. Does the order of each of those elements, do they tell me what the size of the resulting group is? I use size of the group just not to overuse the word order. The answer is no, not really. I mean, you've done examples of this where it's like find 2 elements of order 3 so that their product's order 5 or something like that. So the order of the individual elements does not really tell you what the order of their product is. So in this case, we had 2 order 2 elements that generated a group of order 6. Okay, so that's just some observations to keep in mind, that when we're talking about cyclic groups, the order of the element is the size of the group it generates. Okay, let's have a look. And these numbers are going to mean something to us. They're going to be things that our patterns are going to start to fall out of. So let's look at Z sub 6, groups of integers under addition. So good question, Richard. Is there a general strategy to follow? I am going to show you some strategic ways to figure out, rather than just computing all possible products, some strategies to figure out how big these groups are. But in practice, these are just strategies that work in individual examples. In general, that's a difficult problem to actually figure out the size of the group it generates. Luckily, Sage Math can do this for us if these things get to be unwieldy, too big for us, such as the Rubik's Cube, when we start to do things on the Rubik's Cube. And I've got a little bit of code later on that will, actually, I'm not going to use the code, but I'll talk about the results we get later on. I do have code for other examples, though, so we'll see that. So good question, Richard. I'll keep you to hang on to that one, and then we'll see how we can get these results. So Z6, we got this group under addition. What are the subgroups? Well, 0 generates just the 0 subgroup. What about 2? Well, it would be 2, 4, and 0. So I just keep adding it to itself until I get back to 0, and that gets me all the elements. This would be 3 and 0, and 1 would be 1, 2, 3, 4, 5, and 0, which is all of Z6. What about S10 and these 2 elements, alpha and beta? So here's an example where it comes back to your question, Richard. If we were to try to compute all possible products by hand, we'd probably get exhausted pretty quickly, and we wouldn't anywhere near make a dent in it. So what I've done is I've written down here some Sage code, which says, enter your 2 elements in, A and B, I called them. And then I've used the term, or this function called permutation group. And what it does is I give it the list of elements I want it to use to generate a group. And it generates that group, which we've called H. I could also use this. I could use the subgroup command. They do the same thing in this case. So I would typically more likely use the S10 dot subgroup generated by, is what that really means, A and B. And then I can ask for how big is that group? What is the order? And Sage comes back telling me it's 120. So I can make 120 different permutations by taking all possible products of alpha and beta and their inverses. I can even do more than that. I can ask Sage, for example, compute this product for me. And it'll do it. It'll return it in cycle form. I could also say, consider this element, this 4 cycle in S10. Is it in, so this is a question, in H, and it returns a Boolean value. Is that element in the subset H, in the subgroup H? And it comes back saying, yep, it is. Oh, great. Okay, so I know that's in there. I know I can express that permutation as some products of alpha and betas. It doesn't tell me what product it is. That's a harder problem. If that was an easy one to solve, then doing the Rubik's Cube would be easy. We would just say, is this element a permutation of these 48 stickers? And if it is, return to me the sequence that gives it to me. These kinds of questions are answered in specific cases, but as a general process, no, these are hard questions. So the easy question is asking, is it in there? The hard question is saying, how do you write it as a product? That's a difficult question. So in this next one I've asked, is the 3 cycle 8, 9, 10 in H? And it comes back saying, nope, no, it's not in there. That's false. So the raised to the last 2 is just this last bit here. So if I wanted to raise the whole thing, then I put parentheses around it. So there's an order of operations that gets done here. That exponentiation is being applied only to the b. All right, so now let's have a look at things like the dihedral group. We've got R0, R90, and so on, the horizontal and vertical flips. So we've got H flips and the the vertical flip, and we've got our D flip and our D prime flip. And this says, what is the group generated by R90? Well, that's all possible things we can do by applying R90 to itself over and over again. So I can get R90, R180, R270, and I can get R0. If I just used R180, what are all possible elements I get by, or what's the subgroup generated by R180? It's just R180. R180 times itself, which is R0, and that's it. How about HV? Well, I get H, I get V, I get HV, which is R180, and I get H times H or V times V or R180 times R180. Whichever one you want to look at, I get the identity. So I get these 4 elements by doing H's and V's. And so if I'm only allowed to use H's and V's, I can only produce these 4 elements. And I show just in below how you can get Sage Math to do this. I tell it to only use R0, R180, and H and V. And we see from the table down here that H's and V's and R0s and R180s are all appearing together. And that's the Cayley table for that subgroup. What about in S6 if I take these 3 elements and I want to know, what do I get when I allow for all possible products of these 3 elements? Well, the idea is to note that they are disjoint. So that means they commute. So this is actually quite a bit easier to deal with. Because they commute, I don't have to worry about saying, what is alpha beta? And then answering the question, what is beta times alpha? I don't need to look at changing the orders of how the multiplications are done because it's commutative. So what that means is I only have to worry about the elements alpha, m, beta, n, gamma to the L, where m, n, and L are either 0 or 1. Because they commute, I can always take any product and write it in this form. And whether I use an alpha or not, I either have a 0 for its exponent or a 1. I don't need to use a square or a cube because it's a 2 cycle. And so the 2 cycle, the only thing that's going to affect it is whether I use it or not use it. If I put a cube up there, that's just the equivalent of alpha to the 1. So the thing to note is that what we get here is just m is allowed to be one of 2 values, n can be one of 2 values, and L can be one of 2 values. So that tells us that the order is 8. There's 8 possible elements that this thing generates. And they're written there as in this product notation. Okay. So now I want to get to these structure results. This was just a string of examples just to get familiar with the calculations and whatnot that get done. Now I want to get to the big structure results. And here are the structure results. The first one is to notice the following in all our examples. Whenever I had a subgroup, here I'm at D4 on the top of the page, it has 8 elements. All of its subgroups, it's order 4, order 2, the next one was order 4. They all had this nice property that they were divisors. The size of them divided the size of the original group. Turns out that that's always the case. And this is known as Lagrange's theorem. If G is a finite group and H is a subgroup, then the size of H has to divide the size of G. And now we get something even more from that. I won't prove this result until like chapter 18, but we're going to use this all the time. So the size of the subgroup divides the size of the group. A direct corollary of that is the order of an element. Because the order of an element is precisely the size of the group it generates, so the order of the element is the order of the subgroup it generates, and Lagrange's theorem tells us that that has to divide the order of the original group, it tells us that the order of each element divides the order of the group. And that's a very nice result because it tells us that if I'm in a group, let's scroll back. If I'm in a group of size 8, then I know the order of each of the elements has to be a divisor of 8. It can either be 1, 2, 4, or 8, and that's it. There's no other choices for what the order of an element has to be. So this is a beautiful result that tells us how to focus our attention when trying to determine orders of elements. They have to divide the order of the group. Cauchy's theorem, which is another beautiful result, says that for any prime divisor of the order of the group, there is actually an element that has that order. So it's sort of a converse, a partial converse. The corollary says the order of an element divides the order of the group, and Cauchy's theorem says there's a partial converse to that. If you have a prime divisor of the group, the size of the group, then there has to be an element with that order. So what can we do with this? Well, we can start to uncover things about the Rubik's Cube. So for example, the Rubik's Cube is generated by these moves, R, L, U, D, F, B. And we could ask, well, how big is this? So right now, Sage would tell us the answer, but later on in chapter 20, we'll be able to compute this ourselves by hand. But we'll find that this is 2 to the 27, 3 to the 14, 5 cubed, 7 squared, and 11. So this is the size of the Rubik's Cube group, a huge number. It's at 4.3 times 10 to the 19, a huge number. But what this tells us, so Cauchy tells us that there are elements of orders, so of order 2, 3, 5, 7, 11. It tells us that there are move sequences that you can do on the puzzle that has order 2. You do it and then do it again, you get back to where you started from. Or there's also ones of order 3. If you do it again, and do it a third time, you're back to where you started. And there's elements all the way up to order 11. So that's what Cauchy's theorem tells us. It tells us some structure results already. It doesn't tell us what the element is. It just tells us, yep, you can find a move sequence that if you do it 11 times, you'll get back to where you started. Those exist. What else do we get from this? Well, we get that there is no element of order. Well, let's just pick one. There is no element of order 13. Why is that? Well, if there was a move sequence we could do, and we did it 13 times, we get back to where we started. That means it's an element of order 13. But by corollary 11.4.2 says that 13 has to divide the order of the group. But I just look at the order of the group and I say, nope, 13 doesn't divide that. So there's no element of order 13 since 13 does not divide the size of the group. So these are counting results, and they are immensely powerful for us. Let's do the dihedral group, and I'm going to come back. This is where I can come back with a better answer to your question, Richard, about do we have to compute all products, etc.? We're going to see that we can exploit those results we just had. So here we're looking at the dihedral group D7, so a 7 gone. R is going to denote our one click in the clockwise direction. Fi is a flip over one of those axes from 1 to 7. We could ask questions like, if I took this subset, 1, F1, F3, F5, and F7, is that a subgroup? So this is a set of size 5. There's 5 elements. Is that a subgroup of D7? So I don't want you to, I was going to say, I don't want you to think too mechanically on this. I want you to take a step back and just think higher order perspective. Can this be a subgroup? It's a subset. Can it be a subgroup? Now, your first inclination may be to just start taking products and see if you can get out of that set, in which case that's fine. But there's an even simpler way to see why it's not a subgroup. So I'll write it down. This is our not a subgroup of D7. Why? Well, the size of K is 5. And that does not divide 14, which is the size of D7. And Lagrange's theorem up above says, if it is a subgroup, the size of it has to divide the size of your group. And so it can't be a subgroup because 5 doesn't divide 14. So bang, we immediately get not a subgroup, just doesn't have the right size to be a candidate for being a subgroup. So this also tells us that the only possible subgroups could have order 1, 2, 7, or 14. So let's go ahead and list those out. Order 1, order 7, and order 2. The 14 would be the whole thing. So what would be a subgroup of order 1? Well, what would be the elements of order 1? Those would be just the identity. I think I called it 1 in this case. It's like r to the 0. How about the elements of order 7? Well, the elements of order 7 are going to be r squared, r cubed, r to the 4th, r to the 6th. I don't know why I missed 5, r to the 5, r to the 6th. So those are our elements of order 7. And what about our elements of order 2? Well, those are going to be our F1s, F2s, ... all the way up to F7s. So that's what our results above tell us, is that if we want to know what the order of an element is, it has to divide the order of the group. And the order is 14. So our order of our elements can only be 1, 2, 7, or 14. Once we've listed the elements of order 1, 7, and 2, we see there are none left. There's nothing of order 14. This is the last one I want to end on, is, I'm going to leave this off. What is the subgroup generated by F and R? So now we're back to this subgroup generation. So I'm allowing, and I'll put a F1 here just to be specific, F1. So I want to know, just using a rotation of 1 click and then all powers of that, and a flip F1 and all possible products of those things, what can I generate as a group? Yeah, the whole group. The whole group. And why is that? Well, the thing to notice is that the order of F1, that has to divide the order of the group it's in. So that has to divide the size of this group. So we use the cardinality brackets for the size of the group. So we know that. But this group generated by F1 and R, that's a subgroup of D7. So that has to divide D7. And so what I get is that 2 has to divide this, and this has to divide 14. So I'm looking for the size of the group, is a divisor of 14, but also divisible by 2. And so that means the choices are, this thing is either going to be 2 or 14, because those are my only choices. A divisor of 14, that's also even. That's just 2 or 14. But we also have another thing. We know that I'll put this over here. We also know that the same thing for R. The order of R has to divide the size of F1 and R. And the order of R is 7. So 7 has to divide the size of that group. And so of these two choices, that's the only one divisible by 7. So that's got to be the whole group. The order of this group generated by F1 and R has to be 14. So it's got to be the whole group. So that's how we can use these results. We can, do a similar result here like this. What is the size of this group? If I just use an F1 flip and an F2 flip, what elements can I get? So think in terms of divisibility. The size of this group, so the size of this group is divisible by 2, because F1 divides it and F3 divides it. What else? It's got to be divisible by 2. It's got to divide 14, so it's got to be an even number dividing 14. It's got to be that whole group again. It's not just the reflections, because we've seen above that we can't just have reflections. We sort of partially saw that. But just think, if it was only the reflections, F1 to F7, that would be 7 elements, plus the identity, because it has to be in there. That would be 8 elements, but 8 doesn't divide 14. So that can't be the group. So what we have is that this is divisible by 2, and at least 3. Why is that? Well, it has to have F1, it has to have F2, and it's got to have the identity. So it's got to have at least 3 elements and be divisible by 2. And it's got to divide 14. So it's got to be 14. It's got to be all of D7 again. So these are the counting arguments that we can now start to use. We don't have to do multiplications all the time and find inverses. We can just apply simple counting. It's got the size of this thing is divisible by 2. It's at least 3 because it's got at least 3 elements in it. It's got to divide 14. And so it's all of D7. So I think this leaves us up to, maybe there's one question left on the assignment that we haven't quite got to yet. So what I am going to do, just for the purposes of that assignment question, I'm just going to do a quick recording that goes over this last part of the section. And that way you'll have all the information you need for the assignment question. The last part is just taking these ideas and applying them to the group Z mod NZ.